Okay. So let me make a summary where we are with this topic of IMOT. And as I told you, it's I understand it's quite a topic that needs a bit of effort. And today I would like to dedicate some more time to summarize what we did yesterday. And let me rewrite this relationship here, and which says that FC basically is equal to 1 minus C divided C max to the power of beta K. Okay, so basically what I said yesterday is that by integrating this relationship, we get an estimate of the surface runoff. And my explanation yesterday was not fully clear, as you may remember, because I made a mistake in the picture. And then I would like, yesterday I corrected it, I would like to look at the picture now. And so let me try to enlarge it a little bit, because otherwise here it's... so this is a possible shape for the function FC, which is now depicted in the ordinates, while here in the horizontal axis now we have C. Let me just log out from here, because otherwise it takes some room and it's not efficient. Okay, just 1 second. Here we are, perfect. So now, let's dedicate some more time to try to better understand why the area below this curve, the curve that depicts FC depending on C, is the total runoff from the beginning of the event, and the area that is above the curve up to the level of FC is the storage. So let's look at this area. First of all, this area is computed as the integral of FC. So the area below the curve is the integral between 0, if we assume that this is the value of the storage of C equal to 0 at the beginning of the event. Basically, we integrate from a value of C that is equal to 0. We start the integration from there, and then we extend the integration up to a given value of C. So the integral of this function FC, where I call with the symbol K the variable of integration, the integral of this function is the area below the curve. We know this. And let's see how it is computed. So basically, the integral, as you know, is computed by adopting very small steps of integration. They should be infinitely small. And therefore, for each single step, what do we get? We get a multiplication of the delta C value, because you see that in this case, the step is not of course, infinite here. But in this case, what is the base of this area? The base is C, which is precipitation. As I said, up to the saturation of the basin, the C value is coincident with precipitation, because what is C? Remember, C, we are neglecting evapotranspiration. It's the water storage from the beginning of the event in the unsaturated areas. So what happens is that, let's look at a soil column. You get some precipitation from the beginning of the event, and then this precipitation infiltrates. The model assumes that everything goes into the soil, and therefore up to time t, you get a C P value, which is the cumulative precipitation. It's the total rainfall depth that we got over this column from the beginning of the event. Okay, so this total precipitation is the base of this area. And then it is multiplied by what? By, in this case you have to take an average value of F, which is the fraction of the catchment, the fraction of the catchment area that is already saturated. So you are multiplying precipitation from the beginning of the event times an average value, because you have to take this area is given by an F value which is more or less here, an average value of the saturated area. And therefore, if you multiply rainfall times the saturated area, you get the runoff. So this should allow you to understand that this area is indeed representing the runoff. Now, if we look at the upper part, what is depicted here in pink, what is this? First of all, if you look at this part, it's the storage. Why is that? Because if this is surface runoff, what is above the curve is the product of rainfall times the fraction of the unsaturated area, an average value. So this is the storage. Okay? And you can also see this because if you take the difference between rainfall minus the surface runoff, you get the storage. Indeed. Okay? So it's, let me now show you the other picture here. This should be animated, yeah. Now let's look at this animated picture. Basically, we start from the beginning in which we have the surface runoff here, and then if we add another small part, another small increment, we get another contribution to the surface runoff. And then, when we get to the end of the story, where to C max, where the catchment is saturated, you have computed the total contribution to surface runoff. What is then what happens then if it rains again? If it rains again, everything rains, falls over a saturated area, and therefore everything rains there. It's the rainfall is totally contributing to surface runoff. When you get to the end of the story, let me just show you the steps of this picture, because it's animated and it's useful to see how it evolves, but it's also useful to see how the picture evolves, to see the single steps. So this is the picture. So we start from here. Let me enlarge it a little bit. No, I think it's visible. We start from here. Here we are at the beginning of the event. And then we evolve to here. Just 1 second, I'm trying to enlarge it a little bit. This is fine. And let me modify it to just 1 second in order to make, because I noticed that there is I noticed that there is one thing that we should modify here, and I'm sorry for that, I didn't notice it. And basically the total contribution, the contribution to storage extends up to here. It's because it should be basically rainfall times 1, and rainfall times 1, the area below the curve is surface runoff, and the area above the curve is storage. So let me modify it a little bit, sorry for that. Because, let me modify it just 1 second, we can do it online. Sorry. Let me make it smaller just 1 second, because after I modified it, then I will put directly it on the web. Okay, and then okay, it's the area here, just 1 second. Okay, this is the situation. Okay, and let me better explain then. Basically, here you have rainfall, as I said, the rainfall times the area of the catchment is the total volume of water that rained over the catchment. What is below the curve is the integral, and depicted there, and it's the product of rainfall times the fraction of the saturated area. So this is surface runoff. What is above the curve is the difference between total rainfall minus surface runoff, is the storage. And then it evolves like it is depicted in the animated picture, okay? And basically for the next step you get this. In the next step you get this, and please keep in mind that I still have to correct it, but it's basically extended up to the value of 1. So again, you get below the curve the multiplication of delta rainfall times what? The fraction of the saturated area when you have the delta rainfall. So basically you have an increment of rainfall, and if you multiply this increment of rainfall by the saturated area, you get an additional contribution to runoff. And then what is above the curve up to here, so I still have to correct it, is storage. And if you continue with the integration, you get, of course, if it continues to rain, you get this further status, and this is correct. Basically, here where we are here? We are at a point where rainfall saturated the whole catchment. So we got Cmax. And then here, and again, this is correct, the area below the curve is the total contribution to the surface runoff from the beginning of the event up to saturation. Above the curve, you have the total contribution to storage. What happens now if it rains again? If it rains again, C cannot increase because we got already at the maximum value of C. But ideally, we can represent here an hypothetical increment of C. In fact, here I put in as a label of the horizontal axis, not only C, but also precipitation. They are coincident up to the Cmax value, but once that you got the saturation of the whole catchment, if rainfall increases, Cmax cannot increase. But let's depict here an hypothetical increment, okay, which we can depict here because I allowed also this axis to represent rainfall. So what happens, and you will see it in the animated picture. Basically, you have this additional contribution of rainfall. It's depicted in yellow here because you know, C cannot increase. It's only rainfall that can increase. And you should, in order to compute the surface runoff, you should multiply this additional contribution of rainfall times the whole area of the catchment. In fact, you see that now here we keep the unit value. The whole area of the catchment. Why is that? Because all the catchment is saturated. So basically this is what happens. So it starts raining, you have an increase of C up to a value of Cmax. Along this increase of C, if you compute this integral, you get the area below the curve, and this is the surface runoff, cumulative from the beginning of the event. Then, if you take the difference, C d minus the integral here, the difference is given by the area above the curve, which is the storage. And this is what is reported in my web page. And basically this is what you can see in this animated picture that I bring back. And just be patient because I still have to correct it. Okay? I'm sorry for these needs to adjust these figures because, you know, this is something that is not reported in the literature. In the literature, I will show you what you find. And my aim is to make the concept clearer because I noticed that, you know, getting this concept is not easy. And so I'm developing these pictures now, but sorry, I need to adjust as I teach. As I told you at the beginning of the course, I am developing these lectures by scratch, basically, and sometimes I need to adjust. Okay, yesterday we computed this integral. We computed it, and we finally got to the expression for the water volume, which is this one. It's up here. Yesterday we derived this. And as I said, this is something that is not difficult. And basically, this relationship here allows us to compute, depending on the value of C, the storage in the catchment. The storage in the catchment. Remember that C is the storage in the unsaturated areas, while W is the storage over the whole catchment. So you expect that W is lower than C. You expect this because C, as I said, is the storage in the unsaturated areas, but in the catchment, you always have some saturated areas. So when you compute the overall storage over the catchment, you expect a value that is lower than C. And in fact, if you look at the relationship that we derived for the maximum storage, which is something around here, you see that it's indeed W, it's indeed lower than C, because remember that beta is greater than 0. So when you add to beta, or at least is 0, cannot be negative, when you basically divide C by something that is obtained by adding 1 to beta, you get a reduction. Or at least you have the same value. You have the same value when? This is an interesting question. When you may have the same value of W and C, when you may have the same value of the storage over the catchment and the storage in the unsaturated area. You may have it when you have a potential storage in every location in the catchment that is constant. If it is constant, then of course the average over the catchment of the storage is equal to the storage in each location, because the potential storage is constant, so in every location you have the same storage. Okay, but only when beta is 0. In technical applications, you don't have such a situation. Never, because you always have some spatial variability over the catchment of the potential storage, which means that beta is different than 0. Beta equal to 0, you may remember yesterday, means that you have the same storage over the whole catchment. So it's possible. The model runs if you put beta equal to 0, but it's something that is unrealistic. So what happens in practice, given that beta is a parameter, I told you yesterday, is a parameter to be calibrated, when you calibrate the model, you obtain beta values that are different from 0. This is where we are. So I hope that it's clear what, basically. It's clear that the integral of f gives the surface runoff. And this is, as I said, the key step. Okay, now, if we accept this, then we can compute the surface runoff, as I said yesterday at the end of my lecture, according to, let me write them again, according to two possible contributions. We have one contribution which is given up to complete saturation of the catchment, and this is quite easy to compute. So let's suppose that we are at a stage where it rains, but the catchment is not yet saturated. Okay, let's compute this first contribution. And there are several possible ways to compute this contribution, but I think, first of all, keep in mind that the integral below, the area below the curve, gives the total contribution to the runoff from the beginning of the event. What I usually want to compute instead is at each time step the river discharge. So basically, it is computed by taking a difference. So if I have this situation, this is my FC, and this is C. If I have this situation, and I am a C value, C star, which I depict here, the total contribution to runoff is here. But what I usually want, when I have it at a certain time, is not to compute the total runoff volume from the beginning of the event. I want to compute the river discharge at that time. So what I have to do is to make a difference and take this area here. This is the contribution to the runoff at the time when I get C star. And so basically I have to compute this area and divide this, because this is a volume, divide it by the delta t, the time step. This is what I have to do. So basically, there are possible ways of computing this, and the simplest one is that you compute this first contribution, which I think is called year 1, no, year 2, sorry, year 2. Let me write here, ER2. you make the difference between C at time t plus 1 minus Ct, and this is the difference in rainfall. And then you have to subtract, let me put a square parenthesis here, you have to subtract the difference in storage, t plus 1 minus Wt. Okay, keep in mind one thing. This is still a volume. I didn't say this yesterday. If you want to compute Q at time t, which is the river discharge, is equal to ER2 divided by delta T. Because this is a contribution to the surface runoff at time t, but it's still a volume. It's still a volume. If I want to compute the river discharge, what we call in Italian la portata, you should divide by time, because you may remember that the discharge is volume per unit time. So this is a contribution, but it's still a volume, contribution to volume at time t. If you want to compute the discharge, you have to divide by the time step. And what is the time step? Is simply the difference between, or we may write it in this way, delta t is equal t plus 1 minus t. Delta t is the difference between t plus 1 minus t. And the time step is usually dictated by the time step of observation of your data. So if you apply the model to hourly data, hourly means that the time step is 1 hour, so you will have here 3600 seconds. If you apply the model to daily data, then the time step is 86,400 seconds. So this is, of course, something that you have always to take care. Like in the linear reservoir, I told you, be careful of the units. Same thing here. And in general, my suggestion is when you deal with models, try to be always aware of the units and the physical meaning of what you are computing. So in this case, what you are subtracting, you see it's a difference in storage, so it means that it's a contribution to storage or contribution to surface runoff actually. So you have to divide by the time step. But this is a first contribution, which is computed by simply saying, okay, let me take the difference in rainfall, and this is the total volume that falls over the catchment, and let me subtract the volume that is stored. And what remains is rainfall minus storage runoff. But this works up to saturation, because when you get to saturation, then let's suppose that we already got the catchment saturated, C doesn't increment anymore. Because remember, C is the storage in the unsaturated areas. When everything is saturated, C gets equal to C max, and then that's it. It's stable. So you cannot compute the contribution to storage after saturation in this way. And then for this reason, we introduce this first contribution, which is basically, you see, Ct, and let's suppose that it's equal to C max plus rainfall minus C max, which is what we want to obtain. What is this? It's just rainfall. If you have Ct equal to C max, because I assume that we are already at saturation, C max minus C max is 0, it's rainfall, which is fine. Once the catchment is saturated, everything rains is transformed into runoff. Perfect. And the meaning of this writing here, which includes a maximum, is that, you know, there is an intermediate situation. The intermediate situation is where you are very close to C max, so the catchment it is still not saturated, but then gets saturated after the pulse of rain at time t. So basically, if this happens, here you have something that becomes greater than Cmax after adding rainfall. So you get this exceedance, but only the exceedance, and let me show it here, and you take just it. So let's depict it here. Let's suppose that we are at this stage, and Cmax is here. I give you time to see. So let's suppose that we are at this stage here, and we are at C star, and Cmax is here. So we are still below saturation, but then let's suppose that P is equal to this one. This is PT. Okay? So what happens when it rains this quantity P? Basically, you get to saturation. And then, if we want to depict here the C value is this. So, basically what you do is take C star plus PT minus Cmax. This is what is written there. And then this, what is this? The result of this sum and difference, it is this area. And this is computed through the contribution ER1. You see? CT, let's say that this is C star, plus PT minus Cmax. And this is this area, because this is 1. Okay, but we are still missing a contribution, you may say. We are still missing this contribution here. This is not computed by ER1, but this is computed by ER2. Because it's given by ER2 is here. It's given by CT plus 1 minus CT, which is this quantity here. Because CT plus 1 is Cmax minus C star, so it's this quantity here, minus the storage, and this is the storage. This is WT plus 1 minus WT. So you see that by summing ER1 plus ER2, you get any possible case. Below saturation, you just have ER2. After saturation, you only have ER1. If you have a mix between below saturation and after saturation, you get the combination of the two. Please.
If you first need to reach Cmax, then why isn't it the other way around? Why isn't ER1 the second contribution?
Because if you get the second contribution and you apply just this computation, in your case, let me rewrite it by applying it to our case there. So basically, I hope that you can see here. ER2 is equal to what? So first of all, you have CT plus 1, but CT plus 1 is Cmax. Because you see here, from C star, you get to Cmax. And then C doesn't increase anymore. So CT plus 1 is Cmax, minus C star. Okay, so basically what you get is this difference here. And then you have some storage above here. So basically you have to compute this one minus the difference in storage, and the difference in storage is basically W max minus W star. And in this, by doing that, I subtracted this area here. But then I computed this contribution. I'm still missing the part of rainfall that brings C to saturation. And sorry, that brings D over saturation. So I'm still missing this. So if I computed only here 2, I would compute correctly this contribution of this area, but I'm still missing this one. Because what is this one? Is the rainfall that falls over the catchment when it's already saturated. So this is why I need to add year 1. And what is year 1? If you look at year 1, is just the maximum. So let me delete here and write year 1. Let me prove that year 1 becomes equal to the area of this rectangle. So year 1 is equal to the maximum between what? Between, if we read here, it's basically C star plus rainfall minus C max and 0. So what is C star plus rainfall minus C max? It is this segment here. And in order to get the area